Today's topic is related rates. This corresponds to section 3.7 in our textbook. Related rates is kind of a big topic, so we're going to introduce it in this video and then do a lot more practice in class. So I talked about an implicit differentiation, about the need to take a derivative when there are multiple variables involved. So as systems occur in the world, there are usually many things that are changing at one time. Implicit differentiation and related rates are a way to handle those situations where there are multiple variables, finding one variable to relate them all to. And usually that is time. So as time, that constant change happens, how are these different variables in this single system changing? All of them changing at different rates, but with at respect to the same variable time. So these are usually word problems, and you want to look for keywords that are describing changes. Increasing, decreasing, growing, shrinking, etc. So for example here, John is growing at the rate of 3 inches per year, so growing. We have a positive rate of change. Growing usually means a positive, getting bigger. So the rate of change we're looking at is John, so dj dt, the rate of change of John with respect to time. That would be a positive 3 inches per year, alright? If we look at the second example, my mutual fund is shrinking, because that's happening, by 4 cents per day. So my mutual fund shrinking, getting smaller. So the rate of change of my mutual fund with respect to time, so dmdt, that shrinking, we can represent that in numbers with a negative. So shrinking by 4 cents per day. Examples here, the rate's a little more mathematical application, a dry mathematical application. So the radius of a circle is increasing by 4 feet per hour. So the radius is changing, so the rate to change the radius with respect to t, that's increasing, so by 4 feet per hour. Example D, the volume of a cone is decreasing. So represent the decreasing numerically with a negative. So the rate to the volume, dv dt, negative 2 inches cubed per second. Alright, so look for those buzzwords about that describe rate of change and then represent them numerically. Positives can be positive, shrinking, decreasing, getting smaller, represent those with a negative, and then don't forget your units, okay? So let's look briefly at example 2. So a rectangle has dimensions of 10 by 6. So 10, we'll call that the length. 6, call that the width. Of course, in a rectangle, those are interchangeable, so could be 10 by 6 or 6 by 10, whatever. Get to class. Okay, so formulas for perimeter and area, and then how fast each is changing in terms of L and W. So look at it. In terms of L and W. So L and W are all on one side. the perimeter changing, the area changing. We're going to solve for those because those by themselves. So perimeter, you should know this. Perimeter is adding all the sides, so 2 lengths and 2 widths. If you were to take the implicit derivative of this, so derivative of p, dp dt, and then take the derivative of 2l plus 2w. So 2l becomes 2 derivative of l with respect to t. So dl dt and 2w. So 2 derivative of w with respect to t dw dt. Alright? Area, you should know this. Area, length times width. When we take the derivative, dA, I don't like that d. Oh my goodness. Let's try that again. Okay. dA dt. Oh boy, that one's bad too. Better. Oh, t is poor thing. Okay, so derivative of L times W, that does require a product rule. So if you want to, kind of do the product rule real quick. F is L, G is W, F prime, dL dt, G prime, dW dt. Okay, so you kind of want to work up to doing those mentally, but if you have to write it down, go ahead. Then create the cross. So almost like cross multiplying. Not really, but it feels like that. So you have L dW dt plus W dL dt. So we have our base equations, perimeter and area. We have our derivatives of the base equations, your implicit derivatives, so dp dt, dA dt. So now, look at each situation and then plug in what you need to plug in. So let's look at a couple of these, okay? So length and width are increasing at the rate of 2 inches per second. So increasing, we have a rate of 2 inches per second, okay? Now, the increasing at the rate of 2 inches per second for length and width, those are going to be dL dt and dW dt, okay? So 2 can be plugged in for dL dt and dW dt. So the change of the perimeter, dp dt, so our equation for dp dt, 2 dl dt plus 2 dw dt, and dl dt and dw dt are both 2. So 2 times 2 plus 2 times 2. So we end up with 8 inches per second. Which, if you think about it, can make sense, okay? Every single side of the rectangle is increasing at the rate of 2. So 2, 2, 2, and 2, so overall 8 per second. Oops, now I'm going to change the area. Get your area formula, dA dt. Sorry, your change in area formula, so dA dt. Looking there, we have L dW dt plus W dL dt. So the length, let's go over here, length is 10 the rate to change that to 2. And then we need W, we need the width, so 6. And the rate to change dl dt is also 2. Add those up, you get 32. Careful, it's area. Think about your units, okay? Inches squared per second. So related rates is a way to kind of take complex systems, break it down, and approach them very analytically, and try to be organized in how you do that. Look at the example C. So it's length increasing at 3, so length increasing at 3. So that would be dl dt. So dl, actually, you know what, I'll write it down here. So dl dt increasing at the rate of 3 inches per second. The width decreasing at 3. So down here, dw dt, oh boy, that's an A. dt decreasing at 3. So decreasing, so negative 3 inches per second. And we still have our length and width from earlier. Length is 10. And width is 6. So change of perimeter and change of area. So let's look at those two formulas again. So same situation, but different rates to change. Let's look at that. So 2, and let's see, it's 2 dl dt for dp dt. dp dt equals 2 dl dt. So dl dt is down here 3 plus 2 dw dt. dw dt is negative 3. So multiply and add 0 inches per second, which, when you think about it, kind of makes sense. The length increasing 3, the width decreasing at 3. So overall, no change in perimeter. The two lengths are increasing at the same rate that the two widths are decreasing. So you have a net 0 change. Now change in area. So dA dt. Again, go to our area dA dt formula. Is L dw dt plus W dl dt. So we have our 10 for a length, and then multiply by dw dt. So it's important you write down everything you know. So these variables, you just plug them in as you go. Take your derivatives, then plug in any variables. So dw dt is negative 3 plus length 6 times dl dt 3. Multiply and add, you get negative 12 inches squared per second. Right? Don't forget your units as you do this. And you know what? This kind of makes sense. As the width gets smaller, okay? Remember, it's longer than it is wide. So as the width gets smaller, you're taking away longer rows of square units than if the length gets smaller. So as the width gets smaller, you're taking away more length square units, okay? Alright, so kind of introduction to related rates. take a look at the example, the rest of example 2, then example 3 and 4. So, example 3, look at that also. Example 4, look at that also. And just look at those. The rest of the examples in the notes, we'll look at in class, okay?